Right now, somewhere in Pasadena, a team of engineers is listening to a machine that is 22 billion kilometers away. The signal takes nearly 21 hours to arrive. By the time it does, Voyager 1 is already 1,000,000 kilometers further than when it sent it. You are never hearing Voyager in the present. You are always hearing its past. And sometime in the late 2030s, even that stops. The thread snaps. Silence. And then a question opens up that most science coverage just skips past entirely. What actually happens to it for the next 10 trillion years as the stars die and the galaxy goes cold and the universe slowly stops doing anything at all? Grab something warm. Subscribe if you haven't already. We are going to follow this thing until the lights go out. Part 1. The silence that hasn't happened yet. There is a machine, right now, hurtling through interstellar space at 17 kilometers per second, and nobody alive will ever be able to touch it again. Not theoretically unreachable, not difficult to access. Permanently, physically, cosmologically, beyond human reach forever. And the strange thing, the thing that keeps pulling at me every time I think about it, is that this machine is still technically on. Its transmitter is still broadcasting. A signal, faint as a whisper across a canyon the size of a solar system, is still making its way back to Earth every single day. And somewhere in Pasadena, California, a team of engineers is still listening. That is where we are right now. That is the present tense of this story. Voyager 1 is alive, barely, in the way that a candle is alive when you cup your hand around it in a strong wind, not because the flame is thriving, but because nothing has extinguished it yet. But here is what most people do not fully absorb when they hear that fact. The signal you are receiving today from Voyager 1 left the spacecraft approximately 22.5 hours ago. By the time you process what it sent, Voyager is already another 1.3 million kilometers further away than when it transmitted. You are never talking to Voyager 1 in the present. You are talking to a ghost of it, a version that existed almost a full Earth day before you started listening. And that delay is not a technical inconvenience. It is the universe beginning to tell you something about the nature of contact and what it means for something to exist within your awareness versus outside of it. This is the opening condition of everything that follows. Voyager 1 launched on September 5, 1977, from Cape Canaveral, Florida. It was designed with a nominal mission duration of approximately 5 years. 5 years. The engineers who built it calibrated their expectations around a Jupiter and Saturn flyby, collected their data, and fully expected the spacecraft to fade into irrelevance by the early 1980s. That was the plan. That was the entirety of what was asked of it. What happened instead is one of the stranger accidents in the history of human engineering. The machine simply would not stop working. The power source driving Voyager 1 is a radioisotope thermoelectric generator, an RTG fueled by the radioactive decay of plutonium-238. Plutonium-238 has a half-life of 87.7 years, meaning that roughly every 88 years, half of the remaining fuel stops producing heat. The RTGs convert that heat into electricity. Not a lot of electricity by modern standards. When Voyager launched in 1977, the RTGs were generating about 470 watts, which is roughly enough to power 4 or 5 incandescent light bulbs. Not a computer server, not a car, 4 light bulbs, and even that modest output has been shrinking continuously for nearly 50 years. By the time you are listening to this, Voyager 1's power budget has dropped to somewhere in the neighborhood of 230 to 250 watts. That number is falling every year. The spacecraft's engineering team has spent years doing something that sounds almost poignant when you describe it out loud. They have been selectively turning off instruments, one by one, choosing which scientific eyes and ears to close in order to keep the ones they care most about running just a little bit longer. In 2023, they went through a period where corrupted memory in the flight data system produced months of garbled telemetry. The spacecraft was sending back something, but nobody could figure out what. It took NASA engineers nearly 5 months of forensic troubleshooting, working with documents and design schematics that are nearly 50 years old, to isolate the problem and fix it. The engineers who designed those systems are mostly retired or no longer living. The institutional knowledge is preserved in filing cabinets and aging PDF scans of physical blueprints. And still, somehow, they fixed it. Voyager started making sense again. But the clock on that kind of intervention is running out. Sometime in the late 2030s, the exact year depends on modeling assumptions that different engineers will argue about at conferences. The power output will fall below the threshold needed to operate any scientific instrument at all. The transmitter itself requires power. The heaters that keep the fuel lines from freezing in the interstellar cold require power. At some point, those systems will stop. Not dramatically, not with a final transmission and a ceremonial sign-off. In all likelihood, the signal will simply not come back one day. Ground controllers at the Deep Space Network will wait. They will check their equipment. They will rule out interference. And eventually they will conclude, with as much certainty as the data allows, that Voyager 1 has gone quiet. Here is the question that the entire rest of this story is really asking. Does Voyager 1 end when the signal dies? Or does the silence just mean that we can no longer hear something that is still very much happening? Because the spacecraft will not stop, it will not slow down. It will not break apart on contact with anything, because interstellar space is not like ocean water. It is not full of resistance. It is, for most meaningful purposes, nothing. And an object moving through nothing at 17 kilometers per second will keep moving at 17 kilometers per second for a very long time. The central question threading through every part of this story is deceptively simple to state and almost impossible to truly answer. Voyager 1's cameras were switched off in 1990. It cannot see, it cannot record, it cannot report back on what it encounters. So when we ask what Voyager 1 will see across the next 10 trillion years, and we will ask that question in extraordinary detail, who is actually doing the looking? Hold that question. We are going to need it. Before we get to the long silence of interstellar space, there is a story about how this machine got out there in the first place and the extraordinary chain of physics and timing that made it possible. Because Voyager 1 did not escape the solar system on the strength of its rocket fuel alone, it had help. And the thing that helped it is only available once every 176 years. Part 2. The machine that escaped the solar system. Everything that Voyager 1 has ever done, every kilometer it has ever traveled, every photograph it has ever taken, traces back to a single moment of planetary geometry that the solar system arranges for itself roughly once every 176 years. In the mid-1970s, Jupiter, Saturn, Uranus, and Neptune lined up in a configuration that allowed a spacecraft launched from Earth to use each planet's gravity as a kind of slingshot to arrive at one world, let the planet's gravitational field accelerate it, swing around the far side, and emerge moving faster than when it arrived, on a trajectory aimed directly at the next one. It is called a gravity assist. It sounds simple when you describe it that way, and the underlying physics is not especially complicated, but the precision required to actually execute it, to thread a spacecraft through 4 planetary gravitational fields across a journey of billions of kilometers, using rockets and computers built in the early 1970s, is the kind of thing that, if you stop and think about it carefully, should not have been possible. But it was, and Voyager 1 used it. The spacecraft launched aboard a Titan IIIe rocket on September 5, 1977, from Launch Complex 41 at Cape Canaveral. Voyager 2 had actually launched 16 days earlier, on August 20th, but on a different trajectory slower, designed to eventually reach Uranus and Neptune. Voyager 1 was aimed with a single overriding priority: get to Titan, Saturn's largest moon, as fast as possible and study its atmosphere, even if doing so meant being flung out of the plane of the solar system entirely, with no possibility of continuing to the outer planets. The Jupiter encounter came in March of 1979. Voyager 1 did not just photograph Jupiter from a respectful distance. It dove into the system, flying within 349,000 kilometers of the cloud tops, close enough that the planet's radiation nearly overwhelmed its instruments. What it found there rewrote multiple chapters of planetary science simultaneously. Io, the innermost of Jupiter's large moons, was discovered to be the most volcanically active body in the solar system. Linda Morabito, an engineer working on navigation imaging, noticed a plume on the edge of Io's disk that she initially thought was a background star. It was not. It was a volcano erupting, actively, in real time, photographed from space for the first time in human history. The plume rose 280 kilometers above the surface. The temperature at its vent was measured in the hundreds of degrees. It was the first extraterrestrial volcanism ever directly observed, and Voyager found it essentially by accident. The Great Red Spot, which had been observed from Earth for centuries as a persistent storm in Jupiter's atmosphere, resolved into something almost frighteningly structured. Winds at its outer edge were measured at approximately 1,500 kilometers per hour, not a terrestrial hurricane you evacuate from, but a storm system larger than the entire Earth, rotating continuously, that has existed for longer than the United States, has been a country, possibly much longer. Then came Saturn. Voyager 1 reached Saturn in November of 1980, and what it found there extended far beyond the famous rings. The rings themselves, which from Earth appear as a few broad bands, resolved under Voyager's cameras into thousands of individual ringlets, some braided, some sharp-edged, some showing wave patterns propagating outward from shepherd moons that had not yet been discovered. There were gaps in the rings with precise geometric structures that implied gravitational resonances nobody had fully predicted. Saturn's ring system turned out to be one of the most dynamically complex structures in the known solar system, and it took images taken from a distance of a few 100,000 kilometers to begin to reveal that. But the real prize was Titan. Saturn's largest moon was known from Earth-based observations to have an atmosphere unusual for a moon, and to be surrounded by a thick orange haze that prevented any view of the surface. Voyager 1 flew within 5,000 kilometers of Titan's surface on November 12, 1980, and its instruments confirmed what theorists had suspected. Titan has a nitrogen-rich atmosphere denser than Earth's, laced with complex organic molecules, with methane playing roughly the role that water does in Earth's atmospheric chemistry. The haze was so opaque that Voyager's cameras could not see the surface at all. Titan was both discovered and left mysterious in the same flyby. That mystery would not be resolved until the Huygens probe descended through its atmosphere in January 2005. The Titan flyby dictated the rest of Voyager 1's life. The geometry of getting close enough to Titan required a trajectory adjustment that sent Voyager 1 above the plane of the solar system northward, relative to the ecliptic, on a path that would carry it toward the interstellar medium. There were no more planets to visit, no more gravity assists to perform. From November of 1980 forward, Voyager 1 has been doing something that looks deceptively simple, but is actually one of the most profound physical conditions a human-made object has ever been placed in. It has been falling forward, That framing matters. We tend to think of Voyager 1 as traveling purposefully, directionally on a mission. But travel implies intention, and after Saturn, Voyager 1 had no ability to adjust its trajectory in any meaningful way. Its thrusters, such as they are used only for attitude control to keep the antenna pointed at Earth. They cannot alter the spacecraft's velocity or fundamentally redirect its path. What Voyager 1 is doing now, and what it will be doing for the next 10 trillion years, is something far simpler and far stranger. It is obeying inertia. Newton's first law states that an object in motion stays in motion unless acted upon by an external force. In interstellar space, there are essentially no external forces capable of meaningfully altering Voyager 1's momentum on human timescales. So it moves, not because it is trying to, not because anything is pushing it, because physics simply does not have a mechanism for stopping it. There is one more thing on board that deserves mention here, not because it will matter much to the physical story of what Voyager 1 does across the next 10 trillion years, but because it matters enormously to the philosophical question we are building toward. Voyager 1 carries a gold-plated copper phonograph record, the Golden Record. On it are sounds and images selected to represent life on Earth, spoken greetings in 55 languages, music from dozens of cultures, sounds of wind and rain and whale song and laughter, and instructions for playing the record encoded in pulsar timing. Carl Sagan and his team built it as a message in a bottle for any intelligence that might ever intercept the spacecraft. The record is a beautiful object. It is also a message that, in any realistic astronomical scenario, will never be received. The distances involved are simply too extreme, the probability of interception too minuscule, the likelihood of anything capable of interpreting it existing along Voyager 1's path, essentially zero on any timescale that feels meaningful to imagine. What the Golden Record actually is, if you look at it honestly, is not a communication device. It is a cultural artifact that tells us something about the humans who made it, about their hope, their longing for connection, their instinct to reach outward, even when there is nothing to reach toward. It is the most expensive message anyone has ever sent to no one in particular, and it sits on a spacecraft that is no longer capable of observing anything, moving through a universe it cannot perceive, carrying a record it cannot play. That image, the record, the silence, the inertia, is the frame for everything that comes next. Part 3. The moment we lost its eyes. On February 14th, 1990, Voyager 1 was approximately 6.04 billion kilometers from the Sun, about 40.5 astronomical units. The spacecraft had been traveling for 12 years and was already far beyond the orbit of Neptune. And on that day, at the request of Carl Sagan, the flight team issued a command. They turned the cameras around. Voyager 1 rotated on its axis, pointing its wide-angle camera back toward the inner solar system, and over the course of approximately 3 hours took 60 individual photographs. Those images were arranged into a mosaic, a family portrait of the solar system as seen from deep space. Most of the planets are visible as faint dots against the black. Saturn barely registers. Uranus and Neptune are almost indistinguishable from noise, and somewhere in a beam of scattered sunlight in one frame, so small that you might miss it if you weren't looking for it, is Earth, a pale blue dot, approximately 0.12 pixels in diameter. Sagan wrote about that image in a way that has become one of the most quoted passages in science communication. He described Earth as a mote of dust suspended in a sunbeam, a very small stage in a great cosmic arena. He used it to argue for humility, for the recognition that all of human history, every empire and catastrophe and act of generosity and cruelty, had played out on a speck so small as to be nearly invisible from the edge of our own solar system. What is less often discussed is what happened immediately after those photographs were taken. The cameras were turned off, permanently. The decision was practical, not poetic. Voyager 1's power budget was already tight. The imaging system drew power that could be used for other instruments: the plasma wave spectrometer, the magnetometer, the low-energy charged particle detector, and there was nothing left to photograph. Between the planets and the stars, there are billions of kilometers of essentially nothing, and you do not need a camera to measure nothing. You need instruments that can detect fields and particles and waves, the invisible architecture of interstellar space. So the cameras went dark, and they have stayed dark ever since. Here is the thing that this moment demands we acknowledge, because it is the hinge point of the entire story we are telling. When we talk about what Voyager 1 encountered in interstellar space, the crossing of the heliopause in 2012, the transition from the solar wind to the interstellar medium, we are not talking about things the spacecraft observed in the visual sense. We are talking about things its instruments measured: particle densities, magnetic field orientations, plasma wave frequencies. The data that confirmed Voyager 1 had entered interstellar space for the first time was not a photograph. It was a change in the pitch of plasma oscillations picked up by an antenna. Voyager 1 has not seen anything since 1990. It has sensed, it has measured. But seeing in the sense that most of us mean when we use that word, the sense of forming an image of the surrounding environment that ended with the pale blue dot sequence. And this creates a genuinely strange problem for the story we are about to tell, because the story is framed as a journey, as a traveler moving through space and time and encountering the universe as it changes around it. Every instinct we have about journeys involves a perspective, a pair of eyes, a consciousness experiencing passage through a changing world. Voyager 1 does not have that. It has not had it for decades. When we describe what Voyager 1 will encounter in the next 10,000 years, or the next billion, or the next 10 trillion, when we talk about it drifting through a universe where the stars are dying out and the galaxies are merging, and the laws of physics themselves may begin to undermine the coherence of matter, we are not describing something that Voyager 1 experiences. We are describing something that Voyager 1 exists within, passively, without awareness, without sensation, without any capacity to record or report or witness. The question that is going to follow us through everything that comes next is this: if a spacecraft travels through 10 trillion years of cosmic transformation without anything or anyone capable of observing it, does that journey have a perspective? And if it does not, if the journey is entirely inside the imagination of the humans thinking about it, then who is actually seeing what Voyager 1 sees? That question does not have a comfortable answer, but I want to sit with it as we move forward, because I think the discomfort it produces is more honest than the tidy narrative of an explorer moving through the cosmos with open eyes. The cameras are off, the silence is coming, and whatever Voyager 1 is about to experience, if experience is even the right word, it will experience completely alone. Part 4. The Slow Fade. Here is something engineers do not like to admit publicly, but will tell you in private. They do not know exactly when Voyager 1 will go silent. They have models, good ones, built on decades of real power output data and material science projections and careful accounting of every watt the spacecraft consumes. But the RTG decay is not perfectly smooth. The thermoelectric converters themselves degrade over time in ways that are difficult to model precisely. The heaters that keep certain components from freezing are essential but draw power that might otherwise extend the mission. The exact moment at which the transmitter drops below operational threshold is not a fixed date on a calendar. It is a probability distribution, a range of outcomes that engineers argue about in technical papers and project planning meetings, with the honest answer being something like sometime in the late 2030s, give or take a few years. What is not uncertain is the direction. The power curve goes in exactly one direction, and it does not reverse. Voyager 1's engineering team has been engaged in a quiet, years-long exercise in triage. Every instrument on board costs power. Every heater costs power. The science team has to make regular decisions about what to sacrifice in order to keep what matters running a little longer. In 2019, the heaters on one of the science instruments were turned off to conserve power, and the instrument kept working anyway, which surprised everyone because the temperatures it was operating at were far below what the engineers had considered survivable. The spacecraft occasionally exceeds expectations, but it exceeds them in a universe where the expectations are already very low. Think about what this triage process actually looks like from the outside. Voyager 1 is more than 22 billion kilometers away. A command sent from the Deep Space Network travels at the speed of light and takes approximately 20 hours and 45 minutes to reach the spacecraft. A response takes another 20 hours and 45 minutes to come back. So when engineers want to change something on the spacecraft, flip a switch, reconfigure a power allocation, test a subsystem, they send the command, and then wait nearly 2 days to find out what happened. If something goes wrong with the command, they wait 2 days to discover the mistake, and then another 2 days to send a correction, and another 2 days to find out if the correction worked. The operational loop for troubleshooting Voyager 1 is measured in days, not minutes. This is not the way spacecraft are usually operated. Modern missions have response loops measured in minutes for nearby spacecraft, hours for missions in the inner solar system. Voyager 1 exists in a communication regime that is fundamentally different in character, not just slower, but structurally altered. The one-way light travel time means that Voyager 1 is always, in a meaningful sense, operating in the recent past from the perspective of its controllers. By the time you know what the spacecraft did 10 minutes ago, the spacecraft is already doing something different. The Deep Space Network, the system of massive radio dishes in California, Spain, and Australia that handles communication with Voyager 1, is itself a constrained resource. There are many spacecraft competing for antenna time: Mars rovers, the James Webb Space Telescope, new outer solar system missions. Voyager 1 does not have exclusive access to the most sensitive dishes, and as the signal weakens, communication sessions that were once routine become progressively more demanding in terms of the signal processing required to pull useful data out of the noise. Here is a number that contextualizes the challenge. By the time Voyager 1's signal arrives at Earth, it has spread across a sphere approximately 22 billion kilometers in radius. The power of that signal, spread over that sphere, is roughly 10 to the power of negative 17 watts. That is 100 quadrillionths of a watt. A single modern smartphone transmitting at maximum power puts out roughly 2 to 4 watts. Voyager 1's received signal is more than 10 quadrillion times weaker than your phone call. It is the quietest engineered voice that humanity has ever tried to hear, and it is getting quieter every day. The emotional quality of this phase of Voyager 1's story is unusual. It is not a disaster. Nothing is breaking catastrophically. The spacecraft is performing almost exactly as the physics demands it should. The plutonium is decaying at the rate that nuclear physics dictates it must. The instruments are aging in ways that material science predicted they might. There is no malfunction to diagnose, no engineering failure to heroically overcome. There is only the slow, inevitable retreat of a machine from the edge of human perception. Voyager 1 is not dying in the dramatic sense. It is fading, and there is a difference. A death has a moment. A fading has no clear boundary, just a gradual lengthening of the silence between signals, a growing uncertainty in whether what you heard was really a transmission or just noise, and eventually a decision by the humans on the receiving end to stop calling it contact. The machine, meanwhile, keeps moving. Part 5. The last signal problem. There is a concept in radio astronomy called the signal-to-noise ratio. It is exactly what it sounds like, the ratio of the strength of the signal you want to receive to the strength of the background noise surrounding it. A high signal-to-noise ratio means you can hear the signal clearly. A low one means you are straining to hear something against a constant hiss of interference. When the ratio drops to 1, when the signal and the noise are about equal in strength, you are essentially guessing. You cannot reliably distinguish what the spacecraft sent from what the universe happened to produce at the same moment. Voyager 1 is approaching that threshold. The Deep Space Network's largest dishes, including the 70-meter dish at Goldstone in California, can still maintain lock on Voyager 1's signal as of the mid-2020s. But maintaining that lock requires precise Doppler corrections, adjustments for the fact that the spacecraft is moving, which shifts the frequency of its transmission by a tiny but measurable amount. Those corrections require knowing exactly where the spacecraft is and exactly how fast it is moving. And because Voyager 1's velocity is itself measured by analyzing the signal, you get a circular dependency. The quality of your signal affects the precision of your position model, which affects the quality of your signal corrections. In the 2023 and 2024 period, Voyager 1 experienced exactly the kind of anomaly that illustrates this fragility. A chip in the flight data system began producing corrupted data. The spacecraft was sending something, the signal was there. The carrier wave was present, but the data content was nonsense, garbled, unreadable. For several months, engineers could confirm that Voyager 1 was still alive and transmitting, but they could not extract meaningful scientific information from what it was sending. That situation was resolved, impressively, through creative engineering, but the underlying lesson is important. There is a difference between receiving a carrier signal, detecting that something is out there, and receiving intelligible data. In the final years of Voyager 1's mission, the progression is likely to go something like this. First, science data quality degrades. Then, the margins around maintaining signal lock narrow. Then, the windows of usable contact per day shrink. Then, individual sessions begin producing only partial data returns. Then, the uncertainty in any given session about whether contact was actually made increases to the point where engineers cannot confidently distinguish a successful reception from instrument noise. And then one day, the session produces nothing. The community of engineers working on Voyager 1 has, over decades, developed something that you can only describe as a long-term relationship with the spacecraft. There are scientists who have worked on the Voyager mission for 30, 40, even 50 years. The original project scientists and principal investigators are mostly gone, but a generation of researchers grew up in their careers studying Voyager 1 data. They have watched the spacecraft age in real time, in human time, across the span of their professional lives. They know its quirks, its anomalies, the little signatures in the data that tell you the spacecraft is healthy versus struggling. The psychological weight of the final loss of contact is something that gets discussed quietly in the Voyager science community. Losing a spacecraft is not like losing a loved one. The analogy is imperfect in obvious ways, but the severance of a relationship that has lasted half a century with a machine that has returned more scientific information about the outer solar system than any other instrument ever built carries genuine emotional gravity for the people who have spent their lives in conversation with it. But here is the key thing that the loss of signal does not change. Voyager 1 does not know. The spacecraft has no awareness of whether anyone is listening. It has no sensor for absence. Its transmitter, if it still has power, fires. Its RTG, if it still has fuel above the decay threshold, produces heat. Its inertia, which requires no power at all, carries it forward at 17 kilometers per second through a medium that offers no resistance. The end of contact is entirely an event on the human side of the equation. On Voyager 1's side, there is no equation. There is no side, there is just the continuing physics. And that asymmetry, the fact that Voyager 1's existence becomes entirely independent of human awareness the moment the signal fades, is exactly the condition that makes the next 10 trillion years possible to discuss at all. Because if Voyager 1 required our observation to continue existing, none of what follows would happen. It does not, and it does. Part 6. The point of no return. Imagine a telephone that has been ringing for 50 years. You have been answering it reliably, every day, sometimes multiple times a day, for longer than many of the engineers answering it have been alive. And then one morning, the phone rings, or you think it rings. You think you hear something in the noise, but when you pick up, there is nothing there. Static, cosmic background. The ambient radiation of a universe that has no particular interest in your communication infrastructure. You try again. You point the dish more precisely. You adjust the frequency. You run the noise filtering algorithms at their most aggressive settings. You try again the next day and the day after that. You tell yourself that this might be temporary. There were anomalies before, in 2012, in 2023, and the spacecraft surprised you then, so maybe it will again. But at some point, and there is no crisp moment when this happens, which is almost the cruelest part, the probability assessment shifts. The statistical likelihood that what you are observing is noise rather than signal exceeds the probability that it is signal rather than noise. And the official determination, issued carefully and with appropriate qualification, becomes: contact with Voyager 1 has been lost, not destroyed, not dead, lost. The language is precise, because Voyager 1 is still there. At the moment of final signal loss, the spacecraft will be somewhere in the range of 20 to 24 billion kilometers from Earth, depending on when exactly that moment comes. It will be moving at approximately 17 kilometers per second, a velocity it has maintained with extraordinary consistency, governed by the inertia imparted to it in 1977 and refined by the gravity assists of Jupiter and Saturn. That velocity is not diminishing in any meaningful sense. Interstellar space is not a medium that resists a spacecraft's passage, the way air resists an airplane or water resists a boat. The few atoms per cubic centimeter that constitute the interstellar medium create drag so minuscule that it would take far longer than the age of the universe to produce a noticeable change in Voyager 1's speed. So the spacecraft keeps moving. The silence on Earth is total. The movement in space is unchanged. What is strange about this moment, the moment of final signal loss, is that it represents a rupture in something that has existed since September 5th, 1977. For the entire period between launch and that final silent session, there has been a physical thread connecting Voyager 1 to Earth. Photons, electromagnetic radiation, radio waves carrying data, traveling at the speed of light across an expanding distance. That thread has been fragile for decades. It has been strained and stretched and has required enormous engineering effort to maintain. But it has been real. There has been a continuous chain of causality linking what Voyager 1 does to what humans on Earth observe. When that thread breaks, it does not just mean we can no longer hear the spacecraft. It means that, from the perspective of any information transfer, Voyager 1 might as well be in another universe. Events happening at Voyager 1's location changes in the interstellar magnetic field it passes through, particle interactions at its surface, micro-impacts from interstellar dust produce no effect that propagates back to Earth. The causal connection is severed. Voyager 1 enters what you might call informational isolation. It continues to exist and move and interact with its environment in the minimal ways that a piece of metal moving through near vacuum can, but none of that interaction produces any record anywhere that a human observer could access. And this is precisely where the story becomes genuinely strange. Because everything that comes after this moment, every scenario we are about to describe across the next 40,000 years, the next 4 billion years, the next 10 trillion years, is not observed by anyone or anything. It is inferred. It is reconstructed from physics. It is, in the most precise sense of the word, imagined. The journey ahead is real. The witnessing is entirely in your mind. Part 7. 1. Light day away from home. In the year 2026, Voyager 1 is approximately 1 light day from Earth. That is the distance that light, the fastest thing permitted by the laws of physics, travels in 24 hours. In kilometers, that number is approximately 26 billion. In terms of anything you can relate to intuitively, it is a number that simply does not map onto human experience. There is no metaphor that captures it without distorting it. You can say that if you drove at highway speed without stopping, it would take approximately 60,000 years to cover that distance, but that sentence produces the sensation of a large number without producing any genuine understanding of the scale it describes. What the 1 light day figure actually tells us is something more conceptual than geometric. It tells us that Voyager 1 and Earth have become, in a meaningful, physical sense, temporally separated, not just spatially. Any event that occurs at Voyager 1's location right now will not be detectable on Earth for a full day after it happens. Any instruction Earth sends to Voyager 1 will arrive 1 day after it was sent. The two endpoints of what was once a communication link now exist in what physicists might describe as space-like separation. There is no reference frame from which you can meaningfully say they share the same moment. This temporal separation has been building for decades, of course. Voyager 1 was already communicating with a 20-hour delay when it crossed the heliopause in 2012. The 1 light day mark is not a physical boundary. The spacecraft does not pass through any detectable phenomenon when it crosses it. But it is a useful conceptual marker because it crystallizes something that has been true in principle for a long time. The Voyager 1 that Earth observes and the Voyager 1 that actually exists are no longer the same object. They are separated by an unbridgeable delay. There is a term I want to introduce here that I think is useful for the rest of this story: communication archaeology. When you receive a message from Voyager 1, you are not receiving news. You are receiving a historical document. You are reading an account of something that happened before the message was sent, describing conditions that existed before the transmission, arriving to tell you about a moment that is already 1 day in the past by the time you hear about it. The entire enterprise of monitoring Voyager 1 is, and has been for some time, a form of archaeology practiced on a timescale measured in days. Now project that forward. In a few years, the signal will be gone. In 40,000 years, the spacecraft will be passing through the vicinity of its nearest stellar neighbor. During that epoch, Gliese 445, a red dwarf star in the constellation Camelopardalis. From that position, the light travel time from Voyager 1 to Earth will be measured in years, not days. The spacecraft's position will be inferable from physics, but not from observation. Its state, the physical condition of its metal and circuits, will be entirely unknowable in any empirical sense. The communication archaeology will have given way to something more like theoretical reconstruction. The point here, the thread I want to keep pulling on as we move forward, is that Voyager 1's existence across deep time is not a witnessed journey. It is a calculated one. We are not tracking it. We are extrapolating it from known initial conditions, its velocity, its trajectory, its mass, and composition, and applying the laws of physics to project where it will be, and in what state, across time frames that dwarf the age of civilization, the age of life on Earth, and eventually the age of Earth itself. We are, in other words, running a thought experiment on a real object. And the thought experiment is only possible because the real object is out there right now, existing independently of whether anyone is thinking about it. Hold on to that distinction. It is going to matter more and more as the timescales expand. Part 8. The first deep time leap. 40,000 years. Say that phrase in conversation, and it feels historical. 40,000 years ago, anatomically modern humans had been in Europe for perhaps 10,000 years. The cave paintings at Chauvet were being created. Neanderthals were in their final millennia. The last glacial maximum, the coldest period of the most recent ice age, was still ahead. In the context of Voyager, one's journey, 40,000 years, is the time it takes to reach the first significant stellar landmark. A close approach, and I'm using those words very loosely, to a star called Gliese 445. Gliese 445 is a red dwarf located in the constellation Camelopardalis. It is currently about 17.6 light-years from Earth. Red dwarfs are the most common type of star in the Milky Way galaxy. They are dim, cool, long-lived, and utterly unremarkable to casual observation. In 40,000 years, the combined motion of Gliese 445 through the galaxy and Voyager 1's continued linear trajectory will bring them to within approximately 1.7 light-years of each other. 1.7 light-years. That sounds close in the context of interstellar distances. It is not. 1 light-year is approximately 9.5 trillion kilometers. 1.7 light-years is approximately 16 trillion kilometers. The closest pass between Voyager 1 and the nearest star in its path is about 16 trillion kilometers. To put that in perspective, the entire journey from Earth to Gliese 445 at Voyager 1's current speed of 17 kilometers per second would take about 32,000 years after the closest approach. The solar system, everything from the Sun to the edge of the Oort cloud, spans roughly 1 to 2 light-years across. Gliese 445's gravitational influence at a distance of 1.7 light-years is so minuscule as to be literally undetectable by any instrument Voyager 1 carries or ever carried. The star's thermal radiation at that distance is fainter than faint. This is, by any meaningful measurement, an encounter in only the loosest astronomical sense. Voyager 1 will pass through what is technically the stellar neighborhood of Gliese 445 without any interaction that would change anything about its velocity, its trajectory, its physical state, or its future. And that is exactly the point. Interstellar space is not like ocean space. When we describe the ocean as vast, we mean that it takes a long time to cross. When we describe interstellar space as vast, we mean something categorically different. We mean that the average distance between objects is so large that the objects themselves are essentially irrelevant to each other's existence. Stars, which are in absolute terms enormous. The Sun is about 1.4 million kilometers in diameter, are separated by distances so much larger than themselves that the ratio between stellar size and interstellar distance is roughly comparable to placing 2 grapefruits on opposite ends of a continent and calling them neighbors. This is the moment in the story where human intuition starts to fail systematically. We are built to understand spaces at the scale of landscapes, perhaps at the scale of continents if we stretch. We can intellectually process the distance from Earth to the Moon, 380,000 kilometers, about a second at the speed of light, as a comprehensible quantity because humans have physically traversed it. We can handle the distance from Earth to Mars, hundreds of millions of kilometers, because spacecraft do it routinely. But the distances of interstellar space are not just bigger. They are in a different conceptual category. They are distances at which even the fastest thing in the universe, light, takes years to cross a single step. Voyager 1's passage through the interstellar medium across 40,000 years is, from a physics standpoint, almost entirely uneventful. The spacecraft's velocity does not change meaningfully. Its trajectory follows the initial vector imparted to it in 1977, modified by the gravity assists at Jupiter and Saturn, now simply coasting. The interstellar medium it moves through is extraordinarily thin, roughly 0.1 to 1 atom per cubic centimeter, compared to approximately 10 to the 19th power atoms per cubic centimeter in the air you are breathing right now. The spacecraft is moving through something that is, for most practical purposes, nothing. Nothing slows it. Nothing redirects it. Nothing, in 40,000 years, even notices it. The physical journey is already largely written. What is not written, what has not existed, since the cameras went dark in 1990, is any record of it. Voyager 1 is crossing 40,000 years of interstellar space and leaving no trace of the crossing. Part 9. The galaxy moves without it. Here is a fact that tends to reframe everything else once it lands properly. The Milky Way galaxy is not a fixed backdrop. It is not a stage on which stars sit still while Voyager 1 wanders through them. The Milky Way is a rotating disk of roughly 200 to 400 billion stars, all of them in continuous motion relative to each other, all of them following orbits around the galactic center that take hundreds of millions of years to complete. Our Sun, at its position about 26,000 light-years from the galactic center, completes one orbit approximately every 225 to 250 million years. That orbital period is sometimes called a galactic year or a cosmic year. In the time it will take Voyager 1 to reach the vicinity of Gliese, 40,000 years, the Sun will have moved approximately 40 light-years along its galactic orbit. Earth, and everything that is or was on it, will be 40 light-years from where it is right now. The star that Voyager 1 is heading toward, Gliese 445, will also have moved. The interstellar neighborhood that Voyager 1 is passing through is itself in motion. The entire stellar population of the local galactic region drifting along individual orbital paths around the galactic center. For Voyager 1, this matters in the following way. There is no fixed frame of reference for its trajectory. We describe it as heading outward from the solar system, which is true locally. It is moving away from the Sunday. But in galactic terms, the Sun itself is moving, Voyager 1 is moving, and the destinations it passes near are moving. The spacecraft is not cutting a straight line through a static universe. It is following a complex curve through a rotating galaxy whose structure is itself evolving on timescales of billions of years. Over billions of years, the stellar environment around Voyager 1's trajectory will become unrecognizable. Stars are born and die. The galaxy's spiral arm structure, the density waves that create the characteristic pinwheel shape of spiral galaxies, drifts and evolves. Clusters of stars that are gravitationally bound will disperse over billions of years as perturbations gradually randomize the velocities of their members. New stars will form in regions where the interstellar medium is compressed by those density waves, and some of them will be along or near Voyager 1's extended path. And then, approximately 3 to 4 billion years from now, something genuinely dramatic happens to the Milky Way galaxy, not to Voyager 1 specifically, but to the structure it exists within. The Andromeda Galaxy, currently about 2.5 million light-years away and approaching at roughly 110 kilometers per second along the line of sight, will begin a collision and merger with the Milky Way. This process will take several billion years to complete. Gravitational interactions between the two galaxies will reshape the orbits of stars in both systems. The neat disk structure of both galaxies will be disrupted. The merger will eventually produce a single, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. What does this mean for Voyager 1? In one sense, very little. The spacecraft will be carried along by whatever gravitational environment it finds itself in, but galaxies merging is not like ships colliding. The average distance between stars in a galaxy is so large that the probability of two individual stars actually occupying the same space during a galactic merger is infinitesimally small. The merger is a gravitational reshuffling, not a physical pileup. Stars will be flung into new orbits. The galaxy's shape will change. But most individual stars and the minuscule spacecraft orbiting near their former neighbors will not be directly impacted. Voyager 1 will be carried through this transformation as a passive occupant of whatever gravitational field surrounds it. It will not navigate the merger. It will not respond to it. It will simply exist within a galactic structure that gradually becomes something different over timescales so long that the concept of gradual itself requires redefinition. The spacecraft is not a participant in these events. It is a small piece of metal that happens to be present while the largest structures in the observable universe rearrange themselves. And that, in a strange way, is the most honest description of Voyager 1's entire future. A small, cold artifact, carried through cosmic transformation it cannot perceive, witness to nothing, observed by no one, persisting because physics requires it to. Part 10. The end of the stelliferous era. We need to talk about what the universe looks like in the very long future. Not in geological time, not in the 5 billion-year lifespan of the Sun, but on timescales that most physicists and cosmologists refer to, collectively, as deep time epochs measured in powers of 10 years that are so far beyond human intuition that the only honest way to approach them is to abandon the physicists' expectation of intuition entirely and just follow the physics. The universe, as it exists today, is in what cosmologists call the stelliferous era, the age of stars. It began roughly 150 million years after the Big Bang, when the first stars ignited, and it will end somewhere around 100 trillion years from now, when the last red dwarf finally burns out. We are currently about 13.8 billion years into this era. In terms of the fraction of the stelliferous era that has elapsed, we are at approximately 0.014%. The age of stars has barely started, but the pattern of star formation is not uniform across the stelliferous era. The peak of star formation in the universe's history was approximately 10 billion years ago. Since then, the rate at which new stars are being born has been declining. The universe's molecular gas clouds, the raw material from which stars form, are being consumed by existing star formation and not fully replenished. The reservoir of star-forming material is being used up slowly and inexorably. The largest and most luminous stars, the ones like the blue supergiants that burn hundreds of thousands of times brighter than the Sun, have already been born and died many times over since the early universe. Their lifespans are measured in millions of years, not billions. They are gone. Stars like our Sun, mid-sized main-sequence stars, live for approximately 10 billion years, which is why the Sun is about halfway through its main-sequence lifetime right now. But the stars that will outlast all others by an enormous margin are the red dwarfs, the small, dim, cool stars like Proxima Centauri, our nearest stellar neighbour, and Gliese 445, Voyager 1's first deep-time close encounter. Red dwarfs are extraordinarily efficient at burning hydrogen. A red dwarf with half the Sun's mass will burn steadily for approximately 50 to 80 billion years. The smallest red dwarfs, objects barely above the hydrogen burning threshold, may burn for as long as 10 to 12 trillion years. That is approximately 1,000 times the current age of the universe. On the timescale of the stelliferous era, red dwarfs are the universe's longest burning candles, and they will be the last light to go out. What does this mean for Voyager 1? As the billions of years accumulate, the stellar environment Voyager 1 passes through will become progressively dimmer. The massive, brilliant stars that dominate the visible night sky today will be long gone, their material recycled into neutron stars and black holes. The mid-range stars will have swelled into red giants, scorched their planetary systems, and collapsed into white dwarfs, slowly cooling spheres of electron-degenerate matter, no longer fusing, but still radiating the last of their thermal energy into space at an ever-decreasing rate. And red dwarfs will increasingly dominate the luminous content of whatever is left of the Milky Way or Milkomeda with their faint red light. From Voyager 1's trajectory, the sky will progressively darken, not all at once, not catastrophically, but steadily, over timescales that no biological entity has ever existed to witness. The brilliant blue-white stars will go first, then the yellow-white ones, then the orange ones, until the galaxy is populated almost entirely by dim red points of light, cool, patient, burning their hydrogen at a miserly rate that extends their lifetimes by orders of magnitude compared to the stellar giants that illuminate our sky today. Voyager 1 drifts through this dimming universe unchanged. Its metal, primarily aluminum, titanium, copper, and various alloys, is not chemically reactive in the interstellar medium. Its temperature will approach the ambient temperature of interstellar space, approximately 2.7 Kelvin above absolute zero. The temperature floor, set by the cosmic microwave background radiation, the afterglow of the Big Bang itself, now stretched by cosmic expansion into microwave frequencies, filling the universe with a faint, uniform warmth. As the stelliferous era progresses and stellar radiation becomes increasingly scarce, even the ambient temperature of space may change slightly, though the cosmic microwave background will persist for an extraordinarily long time. Here is a question that should surface naturally at this point, because it is the question the whole story keeps circling back to. As the stars dim and the sky darkens over hundreds of billions of years, is there any way that this transformation is experienced from Voyager 1's perspective? Is there a sense in which the spacecraft encounters the dying of the stars? The answer is no. There is no sense in which Voyager 1 experiences anything. The cameras are off. The instruments, if they were running, would register changes in radiation environment, in particle flux, in magnetic field conditions. But they are not running. They have not been running for the better part of the stelliferous era's duration by the time we reach these epochs. Voyager 1 is an inert object in a darkening universe, carrying no awareness of the darkness. The looking, again, is all happening here, in you. Part 11. The Degenerate Galaxy. 100 trillion years from now, 1 followed by 14 zeros, the last red dwarf star has burned out. Let that settle for a second, because I want you to actually feel the weight of that sentence before we move past it. Not the last massive star, not the last yellow star like our sun. Those have been gone for so long by this point that even the memory of them, if anything were around to have a memory, would be unimaginably ancient. No, the last red dwarf, the most patient, most miserly, most stubbornly persistent class of star the universe ever produced, the ones that burn so slowly and so cool that they stretch their lifetimes to tens of trillions of years, even those are finally gone. The stelliferous era is over. The age of stars, which began roughly 150 million years after the Big Bang, and lasted for a span of time so enormous that our entire current age of 13.8 billion years represents less than 1% of its total duration. That era has ended. The universe has crossed a threshold it will never cross back. What replaces it is what cosmologists call the degenerate era, an epoch that will last from roughly 10 to the 14th years to somewhere around 10 to the 40th years. Those exponents are doing a lot of heavy lifting in that sentence, and I want to be honest with you about what they mean. We are now in territory where human intuition stops working almost entirely. The gap between 10 to the 14th and 10 to the 40th is not a big number. It is not even meaningfully describable as a big number. It is a duration so vast that it contains within it periods longer than everything that came before it, stacked on top of each other, over and over, without end. We are in deep time now, real deep time, the kind that doesn't care what you think about it. In the degenerate era, the dominant objects in the universe are not stars in the conventional sense. There are no fires burning. There is no fusion happening anywhere. The universe has used up its hydrogen, the fuel that powered every star from the very first to the very last, and what remains is what gets left behind when stars are finished. White dwarfs, neutron stars, and black holes. The remnants, the cooling embers and the collapsed cores, and the gravitational wounds that stars leave in space-time when they go. White dwarfs are the fate of most stars, including our own Sunday. When a star like the Sun finally exhausts the hydrogen in its core in about 5 billion years from now, it doesn't just quietly switch off. It swells. It expands into a red giant, growing so large that it engulfs the inner planets. Mercury, gone. Venus, gone. Earth almost certainly gone, or, at minimum, scorched beyond any recognition. The oceans long since boiled away, the atmosphere stripped, the surface temperature of a furnace. The Sun at that stage will be a bloated, pulsing thing hundreds of times its current diameter, burning through helium in its core in a last desperate attempt to maintain pressure against its own gravity. And then that too runs out. The outer layers puff away into a beautiful expanding shell of gas, a planetary nebula, which is one of the most misleadingly named things in astronomy, since it has nothing to do with planets, and what remains at the center is a white dwarf. A sphere roughly the size of Earth, but with nearly the mass of the Sun, composed of electron-degenerate matter so dense that a teaspoon of it would weigh about 15 tons on Earth's surface. It produces no energy, it fuses nothing. It is simply hot, and it spends the rest of eternity doing one thing, cooling down. Very slowly, over timescales that make even the stelliferous era look brief. White dwarfs fade, white to yellow, yellow to orange, orange to red, red to infrared, and eventually, in roughly a quadrillion years 10 to the 15th, they reach a theoretical endpoint that no white dwarf in the real universe has ever actually achieved, the black dwarf. A cold, dark, crystallized sphere of carbon and oxygen sitting at near absolute zero, indistinguishable from the surrounding darkness, radiating nothing, inert, permanent, waiting. Here is the slightly wonderful thing about black dwarfs, and I use the word wonderful deliberately, even though it describes an object that is essentially a cosmic tombstone. None of them exist yet. The universe is not old enough. The coolest, oldest white dwarfs we know of have only had 13.8 billion years to cool, and that is nowhere near enough. Black dwarfs are the universe's most numerous future object. There will eventually be more of them than any other type of remnant, but right now, today, not a single one has ever formed. They are a prediction, a patience test, that the universe is still in the early stages of taking. In the degenerate era, the galaxy, or what used to be the Milky Way, and is now the merged structure astronomers have taken to calling Milkomeda, following its collision with the Andromeda galaxy several billion years prior, is populated primarily by these cooling remnants, along with neutron stars and black holes. Neutron stars are the collapsed cores of more massive stars, objects with roughly the mass of the Sun compressed into a sphere about 20 kilometers across. At that density, individual protons and electrons have been forced together into neutrons, packed so tightly that the density approaches that of an atomic nucleus itself. A neutron star is, in a meaningful sense, a single atomic nucleus the size of a city, spinning sometimes hundreds of times per second, wrapped in a magnetic field so powerful it would strip the iron from your blood from 1,000 kilometers away. They are among the most extreme objects physics permits. And then there are the black holes. At the center of what was the Milky Way sits a supermassive black hole, currently estimated at about 4 million solar masses, a gravitational anchor so powerful that stars orbit it the way planets orbit the Sunday. During the stelliferous era, it grew. It consumed gas, it merged with other black holes during the Andromeda collision, it accumulated mass over billions of years. In the degenerate era, it is the dominant gravitational structure of the remnant galaxy, drawing in whatever matter wanders close enough. It is not luminous, it does not shine, but it holds things together in the way that a drain holds water before consuming it. Black holes do not last forever, though, and this is the part of the story where something that sounds like science fiction turns out to be firmly established theoretical physics. In 1974, Stephen Hawking showed mathematically that black holes are not truly black, that quantum mechanical effects near the event horizon should cause them to emit a faint thermal radiation. The mechanism involves the spontaneous creation of particle-antiparticle pairs near the horizon, where occasionally one member of the pair falls inward while the other escapes, carrying away a tiny quantum of energy. Over time, vast, almost unimaginable time, a black hole slowly loses mass through this process and eventually evaporates completely. A stellar mass black hole takes roughly 10 to the 67th years to fully evaporate. A supermassive black hole of billions of solar masses takes somewhere around 10 to the 99th to 10 to the 100th years. Both of those numbers are so enormous that they effectively define the far boundary of the degenerate era. When the last black hole finishes evaporating, a chapter of the universe closes that began with the very first stars and ends with the last gravitational echo of the last massive one. Now, through all of this, through the century-spanning cooling of white dwarfs into darkness, through the evaporation of the black holes, at timescales that make the current age of the universe look like a rounding error, Voyager 1 is still out there, still moving. Still cold, still intact, it is moving at approximately 17 kilometers per second because nothing has stopped it. There is no mechanism in interstellar space that provides meaningful resistance to a spacecraft-sized object on these timescales. Its metal aluminum, titanium, copper, the specific alloys that engineers at JPL selected in the 1970s, is still structurally coherent, because the interstellar medium does not offer the chemical or physical conditions needed to degrade it meaningfully. The ambient radiation environment is quieter now, with no active stars producing ultraviolet or visible light. There is still the cosmic microwave background, stretched by the expansion of space to even longer wavelengths and lower energies than today. There are still the faint emissions from the last cooling white dwarfs and the occasional, extraordinarily weak photon emitted by Hawking radiation from the remaining black holes, but none of it touches Voyager 1 inch any way that changes anything. The spacecraft drifts. The universe darkens around it. The intervals between events already measured in billions of years grow longer. A neutron star collision, somewhere in the remnant galaxy, happens once every few billion years and releases a brief burst of gravitational waves and heavy elements into an environment with no stars to incorporate them, no planetary systems to rain them down on, no chemistry waiting to be catalyzed. And Voyager 1 is nowhere near it. It is, statistically, in the middle of nothing, as it has been for most of its existence. Here is the sentence that I keep returning to, because I think it is the most quietly staggering fact in this entire story. By the time the last black hole finishes evaporating, Voyager 1 is older than every star that has ever shone in the history of the universe, combined. Older than every planet that has ever formed. Older than the Sun by a factor of tens of billions. It was assembled by human hands in a clean room in California in 1977, by engineers who were probably thinking about lunch at some point during the process, and it will outlast every stellar object the universe ever produced by a margin that has no analogy in any scale of time human beings have ever needed to use. The spacecraft was never meant to last this long. Nobody designed it for the degenerate era. Nobody sat down with a requirements document and wrote, "Must survive until after all stars are extinct." It was designed for 5 years. 5 years, Jupiter, Saturn, done. But physics does not care about intent. Inertia requires no fuel. Persistence, in the absence of any force capable of ending it, is simply the default. Voyager 1 is not surviving the degenerate era through any quality of its own. It is surviving it because the universe has not yet produced a reason for it to stop, and out in the dark, it keeps moving. Part 12. The question of persistence. Here is a question that physicists have been arguing about for decades, and that the standard model of particle physics, the most precisely tested scientific framework in human history, does not currently resolve. Do protons decay? I want you to sit with the strangeness of that question for a moment before we try to answer it, because it is stranger than it first sounds. Protons are not exotic particles. They are not the kind of thing that shows up only in high-energy accelerator experiments or theoretical papers written by people with very long last names. Protons are the positively charged particles at the center of every atomic nucleus in ordinary matter. Along with neutrons, they make up essentially all of the mass of everything you can touch, everything you can see, everything that has ever been built or grown or born on this planet. You are made of protons. The chair you're sitting in is made of protons. The air moving through your lungs right now is made of protons. And Voyager 1, the spacecraft we have been following across 10 trillion years of cosmic time, is made of protons. The aluminum hull, the copper wiring in the circuits, the titanium structural components, the gold-plated surface of the golden record, every atom of every element in every component of that spacecraft is built around a nucleus held together partly by the stability of protons. If protons are not stable, if they can, given enough time, simply cease to be protons, then the question of whether Voyager 1 persists into the far future of the universe is not just an engineering question, it is a question about the fundamental durability of matter itself. So, do they decay? In the standard model of particle physics, the answer is no. The standard model, the theoretical framework, developed across the second half of the 20th century that describes the electromagnetic force, the weak nuclear force, the strong nuclear force, and all of the fundamental particles they act on, contains no mechanism by which a proton can decay into lighter particles. In the standard model, a proton is the lightest particle that carries a property called baryon number, and baryon number is conserved absolutely. You cannot get rid of it. A proton stays a proton because there is simply nowhere for its baryon number to go. It has no lighter state to fall into. It sits at the bottom of a ladder that the laws of physics, as the standard model describes them, do not allow it to descend. But here is the thing, and this is important. The standard model is not the final word on particle physics. It is an extraordinarily successful framework, possibly the most successful predictive theory in the history of science, with some of its predictions confirmed to 10 or 11 decimal places of precision, a level of accuracy that has no parallel anywhere else in human knowledge, and yet it is known with certainty to be incomplete. It does not explain dark matter, which makes up roughly 27% of the energy content of the universe, and which we have never directly detected despite decades of searching. It does not explain the matter-antimatter asymmetry, the fact that the early universe produced slightly more matter than antimatter, which is the only reason anything exists today, including us, and which the Standard Model predicts should not have happened. It does not incorporate gravity in any quantum mechanical way. General relativity and quantum mechanics, the two great theoretical pillars of 20th century physics, remain stubbornly unreconciled, and the Standard Model lives entirely on the quantum side of that divide, unable to speak to the other, which means the Standard Model is a map, and it is an extraordinarily good map of the territory it covers, but the territory is larger than the map. And in the parts of the territory the map doesn't reach, all kinds of things might be happening. Many of the theoretical frameworks that attempt to extend the Standard Model, the broad category of theories called Grand Unified Theories, or GUTs, which try to merge the three quantum mechanical forces into a single, unified description at very high energies, predict that protons do decay, but with half-lives so enormous that they are effectively invisible on any timescale human beings have ever had reason to care about. The current experimental lower bound on the proton lifetime, the minimum age a proton must have, based on the fact that we have never directly observed one decaying, was established by a detector called Super Kamiokande, buried deep under a mountain in Japan, a tank containing 50,000 tons of ultra-pure water, surrounded by thousands of light-sensitive detectors waiting to catch the faint flash of light that proton decay would produce. Super Kamiokande has been running for decades. It has watched an almost incomprehensible number of protons with extraordinary sensitivity, and it has never seen one decay. What that tells us is that if protons decay, their half-life is at least approximately 10 to the 34th years, 100 million times longer than the current age of the universe. If you had been running Super Kamiokande since the Big Bang, you still would not have seen enough decays to draw a statistically meaningful conclusion. On human timescales, and on the timescale of the Sun's life, and on the timescale of the stelliferous era, and on the timescale of the degenerate era we just described, protons are, for all practical purposes, permanent. 10 to the 34th years is longer than the evaporation time of most black holes. It is longer than essentially every physical process we have discussed in this entire video. If someone told you protons were effectively eternal, you would not be wrong for any purpose that involves a timescale humans have previously had to think about. But we are not discussing human timescales anymore. And this is where the story gets genuinely interesting and genuinely unresolved in a way that I think deserves more attention than it usually gets. If protons decay with a half-life of approximately 10 to the 34th years, then, by 10 to the 35th years, one order of magnitude later, roughly 90% of the protons that existed at the start of that period have decayed. By 10 to the 36th years, the probability that any given proton that existed at 10 to the 34th years is still a proton approaches zero. On these timescales, proton decay is not a rare exotic event. It is the dominant process determining the fate of all ordinary matter. Everything made of atoms, every white dwarf, every neutron star, every asteroid, every molecule of gas drifting through the remnant galaxy, and yes, every component of Voyager 1 is slowly coming apart at the most fundamental level possible. The process would not look dramatic from the outside. This is not an explosion. Proton decay does not release enormous energy in a single event. When a proton decays, in the most commonly predicted mode, it converts into a positron and a neutral pion, which itself quickly decays into two gamma-ray photons. The energy released is equivalent to the proton's rest mass energy, roughly 938 million electron volts, which sounds like a lot until you remember that this is the energy of a single subatomic particle. A proton decay event decays about the same energy as a single cosmic ray. Spread across the structure of a spacecraft over timescales of 10 to the 35th years, the effect is not a bang. It is a slow, silent, atom-by-atom dissolution, a gradual softening of structure. Nuclei losing protons one at a time, changing element by element, becoming lighter and then lighter still, until the atoms themselves are no longer recognizable as the elements from which they were forged. What happens to Voyager 1-inch this scenario is something that is genuinely hard to put into words, because we do not have good experiential analogies for it. The spacecraft does not shatter, it does not burn. It simply becomes, over timescales that dwarf everything that came before in this story, less and less itself. The aluminum that was once the hull becomes something lighter. The copper in the circuits loses protons one at a time and drifts toward other elements and then lighter ones still. The specific geometric arrangement of components, the antenna dish pointing toward a sun that no longer exists, the instrument boom extended toward a solar system that has not been a solar system for longer than the stelliferous era lasted, that arrangement slowly loses its material basis. The information encoded in the physical structure of Voyager 1, and there is information there, real physical information, in the specific arrangement of its matter, is not transferred anywhere. It is not preserved. It randomizes. It dissolves into a diffuse cloud of lower energy particles that retain no record of the form they once held. If this happens, then Voyager 1 has an end, not a dramatic one, not one that anyone or anything could witness, but a real one. The spacecraft that left Earth in 1977, that photographed the volcanoes of Io and the braided rings of Saturn and the pale blue dot of home, that crossed the heliopause and entered interstellar space and kept moving for longer than the stars that object, defined by its structure and its arrangement, eventually ceases to be. But here is the other possibility, and I want to give it equal weight, because the physics genuinely does not resolve this. Protons may not decay. The standard model may be correct on this point, even if it is incomplete in others. Baryon number may be a genuinely conserved quantity in nature, not just an apparent one that breaks down at energies we have never probed. In that case, the protons in Voyager 1's structure have no lower state to fall into. They simply persist, indefinitely. In a universe where the black holes have evaporated and the last stellar remnants have cooled past any possibility of detection, and the cosmic microwave background has been stretched by expansion to wavelengths longer than anything we currently have instruments to measure in that universe, Voyager 1 is still there, cold, dark, moving at 17 kilometers per second through a near featureless void, the most structurally complex object in a universe that has otherwise lost almost all of its structure. A relic from an era so remote that no physical process in the current universe retains any memory of it, except this one small, cold, stubbornly coherent piece of metal that will not stop moving because nothing has made it stop. These two futures are radically different. One ends with Voyager 1 dissolved back into the undifferentiated background of a universe in thermodynamic equilibrium. The other ends with Voyager 1 as possibly the last structured object in existence, an accidental monument to a civilization that lasted a few million years on a planet that no longer exists. The physics is honest with us here. It does not know which one is true. And I find that genuinely one of the most remarkable things about this entire story. Not as a failure of science, science is doing exactly what it should, which is telling us clearly where its knowledge ends and its uncertainty begins, but as a fact about the universe. The question of whether matter is permanent or temporary whether structure can persist or must eventually dissolve, whether Voyager 1 has an ending or simply continues forever into a darkness too complete. To imagine that question is written into the mathematics of whatever theory completes the one we have. It has an answer. We just do not know it yet. And the outcome of that unanswered question determines the final chapter of the farthest journey anything made by human hands has ever taken. Part 13. The Universe After Stars. 10 trillion years. I want you to actually try to sit with that number for a moment before we move past it, because I think we have a tendency, when numbers get this large, to just let them wash over us and nod and move on. And I understand why the human brain did not evolve to genuinely feel the difference between 1 billion and 1 trillion, let alone between 1 trillion and 10 trillion. Those numbers exist at a scale so far outside the range of anything our ancestors ever needed to reason about that our intuitions simply do not apply. But let's try anyway, because I think the attempt matters even when it fails. 10 trillion years. Not 10 billion, which is the approximate current age of the universe, the full span from the Big Bang to right now, encompassing the formation of the first stars, the birth of galaxies, the origin of life on Earth, the entire recorded history of human civilization. Not 100 trillion, which is roughly when the last red dwarf star finally burns out and the stelliferous era ends. 10 trillion, 1 followed by 13 zeros. A number that is 724 times larger than the current age of the universe, which is itself already larger than most people can meaningfully conceptualize. If you compress the entire current age of the universe into a single calendar year, so that the Big Bang happened at midnight on January 1st, and right now is midnight on December 31st, then 10 trillion years would be 724 of those years. You would need to run that calendar almost 3 times just to reach the point where the sun forms. You would need to run it over 600 times before Earth appears. And you would need to run it all 724 times before you arrived, at the moment we are describing now, a universe 10 trillion years old, still technically in the stelliferous era, but barely by the thinnest possible margin, with the last active stars already burning at a fraction of the output of anything we would recognize as a star today. This is where Voyager 1 is. This is the universe it is drifting through. The sun has been gone for approximately 5 trillion years. 5 trillion years ago, midway through the period between the universe as we know it and the universe we are describing now, our star exhausted the hydrogen in its core, swelled into a red giant that engulfed Mercury and Venus, and almost certainly Earth, shed its outer layers into an expanding shell of ionized gas that glowed briefly in the dark before dispersing, and left behind a white dwarf, a dense, hot, slowly cooling sphere of electron degenerate matter, roughly the size of Earth, but with nearly the mass of the Sunday. That white dwarf has now been cooling for 5 trillion years. It is still there, technically. It has not vanished. But it is dim and cold, and would require extraordinarily sensitive instruments to detect against the background radiation of the universe. Instruments that do not exist because the civilizations that might have built them do not exist and have not existed for an almost inconceivably long time. Earth itself was consumed somewhere in that red giant phase, 4 to 5 trillion years ago. Not destroyed in any dramatic sense, the matter that made up the planet did not disappear, because matter-energy conservation does not make exceptions for sentimental reasons. The iron and silicon and oxygen and carbon and water and accumulated detritus of 4 billion years of biological activity was absorbed into the expanding sun, heated, stirred into the stellar envelope, and eventually dispersed into the planetary nebula along with the rest of the sun's outer layers. The atoms are still out there somewhere, distributed across a cloud that has long since cooled and thinned to near invisibility. The pale blue dot is not a dot anymore. It is not anything recognizable. It is just atoms, scattered. At 10 trillion years, the stellar population of the universe is a mixture of three things, and none of them are what we would call stars in the full sense of the word. First, there are the last surviving red dwarfs, the smallest, coolest, most hydrogen-efficient stars the universe produces, which can stretch their lifetimes to tens of trillions of years by burning so slowly and so dimly that they produce only a tiny fraction of the light output of a star like the Sunday. At 10 trillion years, these are the only objects in the universe still undergoing hydrogen fusion, and even they are near the end. They burn at a miserly fraction of the luminosity of the stars that lit the early universe. From any distance, they appear as faint, ruddy points of dim red light, separated from each other by voids so large that the word vast does not begin to cover it. They are the last embers. They are the universe's way of holding on to the stelliferous era for as long as physics permits. Second, there are white dwarfs, the cooling corpses of the mid-range stars like our Sun, now so cool and so dim after trillions of years of radiating away their thermal energy that they are approaching true blackness. Some of them may have cooled to the point where they are transitioning toward the theoretical endpoint of white dwarf evolution, the black dwarf, the cold crystallized sphere at near absolute zero. Most are not there yet. Even at 10 trillion years, the cooling process is that slow, but they are getting there, radiating less and less, fading further into the background with each passing billion years. Third, there are neutron stars and black holes, the remnants of the most massive stars, gravitationally significant, capable of distorting the space-time around them, but not luminous in any conventional sense. They do not shine. They do not broadcast their presence. They are simply dense points of extreme gravity in an increasingly dark and diffuse universe, drawing in whatever matter happens to wander close enough, occasionally merging with each other in events that release gravitational waves, but very little light. The sky, from any theoretical vantage point in the universe at 10 trillion years, and I say theoretical because there are no observers, is almost completely dark. Not dark the way a moonless night in the countryside is dark, where your eyes adjust and you see thousands of stars and the sweep of the Milky Way. Dark in a way that has no experiential analogue for any human being who has ever lived. The sparse remaining red dwarfs are so widely separated and so dim that an observer in interstellar space would see perhaps a handful of isolated points of faint red light in an otherwise featureless black sky. No Milky Way. No galaxy visible to the unaided eye. No dense, luminous regions of star formation. Just the dark and a few dying coals glowing at the very edge of detectability. The brilliant, star-filled sky that humans evolved under the sky that gave rise to every mythology and navigation system and astronomical tradition in human history was a feature of the early universe. We live in the photon-rich middle age of the stelliferous era, where star formation is still ongoing and the products of 10 billion years of stellar evolution are all visible at once. That sky, the one you can go outside tonight and look up at, is a temporary condition. The universe at 10 trillion years is not the place human vision evolved to look at. It is a place our eyes, calibrated for a medium-age star-forming cosmos, would find almost incomprehensibly empty, and somewhere in that near darkness, still moving, is Voyager 1. Here is the sentence I want you to really sit with, because I think it is the most quietly astonishing single fact in this entire video. At 10 trillion years, Voyager 1 is older than any luminous object currently existing in the universe. Every active star, every object still undergoing fusion, still producing light, still doing the thing that stars do, is younger than this spacecraft, not younger than the universe. Younger than Voyager 1, the universe at 13.8 billion years, built this machine, and at 10 trillion years, the machine is still there, while essentially everything else the universe built along the way has faded. The spacecraft's temperature has equilibrated over these immense timescales with the ambient radiation environment of the universe around it. That ambient temperature is set by the cosmic microwave background, the thermal afterglow of the Big Bang, the faint, uniform glow of photons that have been traveling through the universe since it was 380,000 years old. Right now, in the present-day universe, the cosmic microwave background has a temperature of about 2.7 Kelvin, 2.7 degrees, above absolute zero, the coldest temperature thermodynamics permits. That is already extraordinarily cold. A room temperature object at about 293 Kelvin is more than 100 times warmer than the cosmic microwave background. But the universe at 10 trillion years is colder still. The cosmic microwave background does not stay at 2.7 Kelvin forever. As the universe expands, the wavelengths of its photons stretch, their energy decreases, and the effective temperature of the background radiation falls. By 10 trillion years, the CMB has been redshifted by cosmic expansion to even longer wavelengths, shifted out of the microwave band and further into the radio band, and its effective temperature is lower than it is today. How much lower depends on the rate of cosmic expansion, which depends on the nature of dark energy, which is one of those fundamental questions the physics community is still actively working on. But colder, measurably, definitively colder. Voyager 1 sits at that temperature. Not because anything froze it, not because any specific event cooled it down, but because 10 trillion years is an almost incomprehensibly long time for a thermal equilibrium to establish itself, and an object in deep space with no internal heat source and no nearby stars to absorb radiation from will, given enough time, simply become the same temperature as the universe around it. The spacecraft is as cold gets in this epoch. Cold in a way that no laboratory on Earth has ever achieved. Cold in a way that the engineers who built it, working in a clean room in Pasadena in 1977, could not have imagined and would not have had any reason to think about, and it is still moving. Still following the trajectory imparted to it by a Titan 3E rocket on the 5th of September 1977, modified by the gravitational assists of Jupiter and Saturn and the accumulated gravitational perturbations of 40-plus stellar close approaches and one galactic merger, but fundamentally still the same vector. 17 kilometers per second, through a universe that has almost entirely forgotten how to produce light. The cameras have been off for 10 trillion years. There is nothing to see. There is, in the most literal sense, almost nothing to see. And yet here we are, seeing it anyway, because the looking, as it has always been in this story, is happening on our end. Part 14. The Era of Almost Nothing. Beyond 10 trillion years, pushing past the last of the red dwarfs, past the cooling of the white dwarfs into darkness, past the slow gravitational dissolution of whatever remains of the galaxies, the universe enters a phase that cosmologists describe with a phrase that sounds almost peaceful, the approach to thermal equilibrium. It is not peaceful, or rather, it is peaceful, in the way that a room in which nothing has moved for 1 billion years is peaceful. Not calm, not restful, just still. A stillness that has no relationship to anything living or dynamic or eventful. A stillness that is the universe's version of having nothing left to say. Thermal equilibrium is a concept from thermodynamics, which is the branch of physics that deals with energy, heat, and the direction that physical processes run. The core idea is this: any closed system, left alone long enough, will eventually reach a state where energy is distributed as uniformly as possible, where every temperature gradient has flattened, where every pressure difference has equalized, where every difference between one region and another that could have driven a physical process has been smoothed away. At that point, there are no more processes, not because the laws of physics have changed, not because something catastrophic has happened, but because all processes, every physical event of any kind, require a gradient. They require a difference. They require that something, somewhere, be out of equilibrium with something else. Remove all the gradients, and you remove all the events, and what you are left with is a universe that exists but does nothing, persists but never changes, continues but has nothing to continue doing. The technical name for this endpoint is heat death. It is one of the more unfortunate names in cosmology because it sounds like the universe gets hot and explodes, which is exactly wrong. The universe does not get hot, it gets uniform. The heat death is not a temperature spike, it is the final, total equalization of temperature across all of space at an extremely low value, approaching but never quite reaching absolute zero. The word death refers not to a dramatic ending, but to the death of the capacity to do thermodynamic work. The universe cannot do anything useful with energy if all the energy is at the same temperature. This is the same reason you cannot run a steam engine if the boiler and the condenser are at the same temperature. The gradient is what does the work. Eliminate the gradient, eliminate the work. Eliminate all the gradients everywhere forever, and you have eliminated the possibility of any event, any process, any change of any kind throughout the entirety of existence. The universe is not quite a closed system in the strict thermodynamic sense, because cosmic expansion continuously changes the geometry of space. It is not a box with fixed walls, and the expansion itself introduces complexities that make a perfect thermodynamic analysis difficult. But the tendency toward equilibrium is real. It is built into the second law of thermodynamics, which is one of the most robustly verified principles in all of physics, and which states, in its most general form, that the entropy of an isolated system never decreases over time. Entropy is, loosely, a measure of disorder of how uniformly energy is distributed, of how many equivalent ways the system's components could be arranged. The second law says entropy goes up, always, over time, without exception, and a universe trending toward maximum entropy is a universe trending toward maximum uniformity, which is a universe trending toward heat death. The timeline for this is almost beyond description. By 10 to the 40th years, a number so large that writing it out in full would require 40 zeros and still not convey any intuitive sense of its scale. Most of the organized structures we have been discussing are gone. The white dwarfs have cooled to near absolute zero black dwarfs, or are very close to it. The neutron stars are dark and cold. The stellar remnants that once anchored galaxies are no longer gravitationally bound to any recognizable structure, because the slow process of gravitational evaporation, in which random gravitational interactions over vast timescales gradually kick objects out of their mutual orbits, has dispersed them across distances so large that galaxy is no longer a meaningful word. What remains in the universe at this epoch are primarily black holes, the supermassive ones that anchored galactic centers slowly, glacially evaporating via Hawking radiation. And here I need to spend a moment on what slowly actually means in this context, because the word is doing extraordinary work in that sentence. A supermassive black hole with a mass of 1 billion solar masses takes approximately 10 to the 97th years to evaporate completely via Hawking radiation. The mechanism, as we discussed earlier, involves quantum mechanical particle-antiparticle pairs appearing near the event horizon, with one member falling in and the other escaping, effectively carrying mass energy away from the black hole one quantum at a time, at a rate so unimaginably slow that for a large black hole, individual Hawking photons are emitted with intervals of millions of years between them. A single photon, every million years, from a black hole that will take 10 to the 97th years to fully evaporate. The process makes continental drift look frantic. It makes the cooling of white dwarfs look urgent. But it happens. Slowly, across timescales that span from 10 to the 40th years to somewhere around 10 to the 100th years, every black hole that exists at the beginning of this era will have evaporated. Their mass energy is returned to the universe not as light in any conventional sense, but as extremely low-energy photons and particles, electrons, positrons, neutrinos, all moving at nearly the same energy, all contributing to the gradual homogenization of the universe's energy content. The last black hole to evaporate will do so in a universe that, outside the immediate vicinity of that event, is already so close to equilibrium that the distinction barely matters. And what replaces the black holes and the white dwarfs and the neutron stars and every other organized structure the universe has ever produced? Something that is not nothing, but is very close to nothing from the perspective of anything that might want to happen. A diffuse, near-uniform background of photons, electrons, positrons, and neutrinos, all at very nearly the same extremely low temperature, all expanding outward into an ever larger and ever colder space. No gradients worth mentioning, no events worth noting, no processes running anywhere. Just the quiet, cold, featureless persistence of a universe that has exhausted itself. This is heat death, not an ending. Just a final, permanent stillness. And Voyager 1, if its protons are stable, if its material structure has survived, is still there, 17 kilometers per second, still moving, through a universe that is, for all meaningful purposes, nothing. I want to think carefully about what this actually means, because I think it is the most philosophically interesting thing in this entire story, and it deserves more than a passing mention. In a universe approaching thermal equilibrium, a universe in which every gradient has flattened and every organized structure has dissolved, and nothing is happening anywhere, Voyager 1 represents something that has no analogue anywhere else in the observable universe at that epoch, a region of space that is not in equilibrium. Its material structure is ordered, atoms in specific crystalline lattice arrangements, maintained by electromagnetic interactions that require no energy input to sustain, alloys with defined chemical compositions, geometric structures, an antenna dish, an instrument boom, the flat circular face of the golden record, with specific shapes that encode, in their physical arrangement, information, real physical information. The information that those atoms are here, in this configuration, rather than distributed randomly across the diffuse background. In information theory terms, Voyager 1-inch the far future universe is an anomaly, a low-entropy island in a maximum entropy sea, not because it is doing anything, not because any process is running inside it, but simply because its atoms are not where thermodynamics would put them if it had gotten its hands on them. They are arranged, they are structured, they are, in the most literal physical sense of the word, meaningful in that they carry more information than a random distribution of the same particles would carry. The universe is not aware of this. There is no mechanism by which the universe at 10 to the 100th years registers Voyager 1's existence. There are no observers. There are no processes capable of interacting with the spacecraft in any way that would propagate information about its presence anywhere else. It is physically isolated in a universe where physical isolation is the normal condition of everything that still exists. It is causally irrelevant to the near-featureless background it moves through. No one is looking, nothing is listening. Nothing can be affected by the fact that Voyager 1 is there, and yet it persists, not because of anything special about it, not because the universe has chosen to preserve it, but because persistence, in the absence of any destructive force, is simply what matter does. Inertia requires no fuel. Maintaining a crystal lattice requires no energy input if nothing is trying to break it. Continuing to move requires nothing at all, because Newton worked this out in the 17th century and the universe has not revised his first law. An object in motion stays in motion. That is not a metaphor, it is not an inspiration, it is a description of how space-time works. Voyager 1's journey across 10 trillion years and beyond through the degenerate era, through the black hole era, to the doorstep of heat death, is not a story the universe is telling. The universe does not tell stories. It does not have intentions, or narratives, or a sense of drama. It has laws and initial conditions, and the working out of one through the other across timescales that dwarf anything a human being has ever needed to think about. What happened was this. In 1977, a group of human beings made a decision to accelerate a small machine to escape velocity and point it toward the outer solar system. That decision set an initial condition: the laws of physics, inertia, gravity, the nuclear decay curve of plutonium 238, the electromagnetic stability of metal lattices took that initial condition and ran it forward. Everything that followed, every kilometer traveled, every stellar encounter, every galactic upheaval, the spacecraft was carried through without knowing it. The slow darkening of the universe around it, the evaporation of the last black holes, the approach of the final stillness, all of it is just the working out of that one afternoon in September of 1977, when a rocket left a launch pad in Florida. The universe is not telling a story about Voyager 1. We are. And the reason that matters, the reason it is worth saying explicitly at the end of all of this, is that the story is not nothing. The looking is not nothing. The fact that a species on a pale blue dot spent time imagining where their small machine was going, across timescales their minds were never built to handle, because they found it beautiful and worth understanding, that is not an incidental detail. That is the only perspective from which any of this is a journey at all. Take that perspective away, and there is no journey. There is only a trajectory. The journey is ours. It has always been ours. And right now, while the transmitter is still on, and the signal is still coming, and the late-night engineers at Goldstone are still listening, while there is still a thread, however thin, connecting us to the farthest thing we have ever made, that fact feels worth sitting with. Part 15. The Final Paradox. Who is seeing this? Let us come back to the beginning. Not the beginning of the universe, not the beginning of the solar system, not even the beginning of the Voyager program. The beginning of the specific thing this whole video has been quietly circling from the very first minute. The thing that makes this story different from every other story about a spacecraft traveling through space. In 1990, a team of engineers at NASA's Jet Propulsion Laboratory sent a command to Voyager 1, 6 billion kilometers away, and turned off its cameras, permanently. The imaging system, the instrument that had produced the photographs of Io's erupting volcanoes, of Saturn's rings, resolving into thousands of individual braided ringlets, of the pale blue dot of Earth, suspended in a beam of scattered sunlight at the edge of the solar system, went dark. Not temporarily, not as a precaution, not pending a reboot. Dark in the way that a decision is dark. Intentional, irreversible, done. In the 35 years since that command was sent and received, Voyager 1 has continued to do what it has always done: move. It has crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, becoming the first human-made object to enter interstellar space. It has reached a distance of more than one full light day from Earth, a distance so vast that the signal carrying any information about its current state takes over 20 hours to arrive here, meaning we are always, in a real physical sense, talking to Voyager's past rather than its present. It has continued to transmit data plasma wave measurements, magnetic field readings, particle counts through the handful of instruments, still drawing power from its slowly decaying RTGs. And in all that time, across all those billions of kilometers, and all those decades of drifting further from everything we have ever known, it has not seen anything. I want to be precise about what I mean by that, because it matters for everything that follows. The interstellar medium Voyager 1 has been traveling through is not empty in any absolute sense. It has structure, it has particle densities that change as the spacecraft crosses different regions. It has magnetic field orientations that shift as Voyager moves through the local interstellar environment. It has plasma wave activity that Voyager's instruments have measured and that has produced genuinely important science, including the data that confirmed, in 2012, that the spacecraft had actually crossed the heliopause and entered interstellar space for the first time in human history. That confirmation did not come from a photograph. It came from a change in the pitch of plasma oscillations detected by an antenna, a sound, essentially. An invisible quantity rendered as a number, then as a graph, then as a conclusion in a peer-reviewed paper. The universe, as experienced by Voyager 1's surviving instruments, is a universe of invisible quantities, field strengths, particle counts, frequency readings, not images. Not observations in the visual sense that the word observation usually implies. Numbers that require human interpretation to become knowledge, and human imagination to become understanding. And now, even those instruments are almost out of power. So here is where we are, after everything we have covered in this video. We have followed Voyager 1 from its launch on a September afternoon in 1977, through its encounters with Jupiter and Saturn, and the discovery of Io's volcanoes and the braided structure of Saturn's rings. We have followed it through the decision to turn off its cameras and take one last look back at the pale blue dot. We have followed it through the crossing of the heliopause and into interstellar space. We have projected its trajectory forward through 40,000 years to its closest approach to Gliese 445, through billions of years of galactic evolution, through the Andromeda collision, through 10 trillion years of the universe's slow dimming as the last stars exhaust themselves and go dark. We have described the degenerate era and the cooling of the white dwarfs toward their theoretical black dwarf endpoint. We have sat with the open question of proton decay and what it means for whether Voyager 1 has an ending or simply continues forever into a universe that has run out of things to do. We have traced the approach to thermal equilibrium and the concept of heat death, the final stillness of a cosmos that has exhausted every gradient that could have driven any process anywhere. And through all of that, every epoch, every billion years, every order of magnitude on the timeline, there has been no sensor, no instrument, no mechanism on board Voyager 1 that records any of it. The cameras went dark in 1990. The last science instrument goes silent, sometime in the late 2030s. For the entire remainder of the timeline we have described for 10 trillion years, or 10 to the 100th years if we follow the physics to its logical endpoint, Voyager 1 moves through the universe in total informational darkness. It does not observe the last stars going out. It does not register the merger of the Milky Way and Andromeda. It does not detect the evaporation of the last black hole. It does not experience the approach of thermodynamic equilibrium. It does not, in any meaningful sense, experience anything. And yet here we are, talking about it, in extraordinary detail, for the better part of an hour. I think that deserves a moment of honest examination, because it is the thing about this story that I find most genuinely interesting, and also the thing that most popular coverage of Voyager sort of slides past without stopping to look at directly. Everything we have described, every stellar encounter, every galactic upheaval, every epoch of cosmic evolution, exists as a journey only in human consciousness. not in Voyager 1's. The spacecraft does not have a journey in any phenomenological sense, any more than a rock rolling down a hill has an adventure. It has a trajectory. It has a physical history that the laws of physics can calculate with reasonable confidence given its known initial conditions. It has a future that we can project forward using the same laws. But the narrative, the sense of moving from here to there across the eons, of passing through a universe that changes around it, of being a traveler in deep time, that is something we are constructing. That is a product of human minds projecting awareness outward onto an object that has none, following it with imagination because we cannot follow it with anything else. Carl Sagan understood something about this asymmetry when he chose to write about the pale blue dot image rather than simply describing it. He could have written a technical caption: Earth, imaged from approximately 6 billion kilometers, subtending approximately 0.12 pixels in the wide-angle camera frame, visible in scattered sunlight from the camera's proximity to the Sunday. That would have been accurate. It would have conveyed the information. But Sagan understood that the information was not the point. The meaning was the point. And the meaning, the humility, the vertigo, the almost physical sensation of scale that the image produces does not live in the photograph. It lives in the people looking at it. The photograph is pixels. The meaning is constructed by the looking. Take away the lookers, and you have a data file. The pale blue dot only becomes the pale blue dot when a human being looks at it and understands what they are seeing. The same principle applies here, expanded to a scale Sagan never directly addressed. Voyager 1's 10 trillion year journey through an aging universe is real in every physical sense. The trajectory is real. The physics is real. The spacecraft is genuinely out there right now, at this very moment, moving at 17 kilometers per second through the local interstellar medium, approximately 22 billion kilometers from Earth. All of that is unambiguously, concretely, measurably real. But the experience of that journey, the sense of passage, of witness, of something moving through a universe that transforms around it, that exists only here, in the people thinking about it. In you, right now, following it forward in your mind across timescales, your mind was never built to handle, because something about it compels that following, even when comprehension fails. And I want to say something about that compulsion, because I think it is worth naming directly. In a universe that is running down, moving from the extraordinary complexity and energy and structure of the early cosmos, through the stelliferous era's 10 trillion years of starlight, through the long cooling of the degenerate era, toward the final featureless stillness of heat-death consciousness, is one of the stranger detours. It is not obvious, from any physical first principles, that the universe should produce entities capable of projecting awareness outward across 10 trillion years to a machine that cannot feel or think or know. It is not obvious that the universe should produce entities for whom the journey of an unconscious spacecraft matters. The laws of physics do not require it. Thermodynamics does not predict it. And yet here we are, doing exactly that, because we cannot seem to help it, because the wondering seems to be part of what we are. Voyager 1 does not need us to think about it. Its inertia requires no audience. Its trajectory does not depend on being observed, does not change when we look away, does not care whether the last engineer at JPL, who still remembers its telemetry signature, eventually retires and is not replaced. The stars will go out on their own schedule. The black holes will evaporate on theirs. The universe will approach its equilibrium state with complete indifference to whether a species on a pale blue dot spent time imagining what their small spacecraft was passing through on its way to the dark. But here is what I keep coming back to every time I sit with this story. The fact that we do imagine it, that we built the spacecraft and pointed it outward and listened to it for decades and then continued to think about it long after the listening stopped, continued to follow it in our minds, into epochs we will never see, Continue to care about where it is and what it passes through in a universe that will not remember us, that seems like it means something. Even if it only means something to us, even if the universe has no mechanism for registering the fact that we cared, even if the caring produces no effect on anything outside the minds that are doing it, because this is the window, right now. This specific period, the stelliferous era, the age of stars, the brief warm chapter of cosmic time, when the universe is producing enough light and energy and complexity to give rise to things that can wonder about it. This is the window during which the wondering is possible at all. The universe is not always producing creatures capable of following a spacecraft across 10 trillion years in their imagination. It is doing it now, briefly, in this narrow band of cosmic time, when the conditions are right, when there is enough energy and structure and warmth for biology and chemistry and consciousness to exist and ask questions about things that cannot ask questions back. That window will close. Maybe in 1,000,000 years, maybe in 1,000,000,000, maybe sooner. The timeline of Earth's habitability is its own uncertain calculation. But at some point, the universe stops producing the kind of complexity that produces the kind of wondering that makes this conversation possible. And when it does, Voyager 1 will still be out there, still moving, still intact if the protons hold, still carrying the golden record that no one will ever play. But there will be no one to imagine it, no one to follow it forward, no one for whom the journey means anything. Right now, there is. Right now, the cameras are off, and the signal is fading, and the spacecraft is falling forward through a universe that will outlast everything we have ever known by a margin we cannot fully conceive. And somewhere, in all of that immensity, in all those zeros on the timeline, in all that dark and cold and silence that stretches forward further than the human mind can genuinely follow, the looking is happening right here, in you. That is who has been doing the looking this entire time. That is the only answer to the question we asked at the very beginning, when we noted that Voyager's cameras were switched off in 1990, and asked, who is actually doing the looking when we describe what it sees across the deep future? You are. We are. The only perspective from which any of this is a journey rather than just a trajectory is this one, human, brief, unreasonably curious. Unable to stop following something into a dark it will never report back from. And when the last transmitter goes quiet and the last instrument shuts down, and Voyager 1 passes beyond every threshold of human contact into a silence that will last longer than the stars, the looking will be the only journey it ever really took. That is the whole story. That has always been the whole story.